Here's a few more example problems to apply what you know about force of friction. So here's a case where we have to do something of a proof. So we know the result we're trying to get. We just have to show how that result comes to be. So we have a block labeled as block number 1 that hangs vertically. So there's a force M1G pulling down. There's a force we'll call T1 pulling up. Now there's no guarantee that the tension in string segments 1, 2, or 3 have the same value. And I'm not real happy with this free body diagram. Let's make sure this looks like equilibrium so that the force vector pointing up is equal to the force vector pointing down. That's the nature of this whole problem, right? Is how much friction? What's the minimum amount of static friction that keeps the system at rest or in equilibrium? So I'll make a free body diagram for block number 2. There's a normal force pushing up. M2G pulls down. There's a tension pulling to the right, and that tension isn't necessarily the same as this tension, so we'll label these tension 1 and tension 2. And then there has to be some force back to the left to maintain equilibrium, and that, of course, is this force of friction. So the force of friction is less than or equal to mu static times normal, but because we're trying to make this a limiting case problem, here we'll say this force of static friction is equal to mu s multiplied by n if that static coefficient represents the minimum possible value. Okay, and then we can label an angle theta right here. Let's try something. Let's make a free body diagram for this knot right here. So there's an amount of force that pulls at the knot to the left, but that's the same as this tension T number 2, right? There's just some amount of tension throughout this string, so it pulls block 2 to the right, and it pulls this knot to the left, so there's T2. But in turn, isn't T2 have to be equal to the force of static friction, which is mu s times n? So if we want, we can just label it as such. This is mu s times n, but n is mg. Okay, likewise, there's a force pulling down, but that's the same as this tension number 1, which in turn is the same as M1G. So I'm going to label that as M1G. And then lastly, there's a third amount of tension pulling up into the right, and we can't call that thing anything other than T3. So this free body diagram is unresolved. Let's make it a resolved free body diagram. So we have mu s times M2G pulling to the left. We have M1G pulling down, and then we have another force at an angle, and we can break that into components by showing our x and y axes. So there's a component that pulls to the right, and there's a component that pulls up, and hopefully this all represents equilibrium. Of course, the component that pulls to the right would just be t times the cosine of theta, and the one pulling up is t times sine theta. I guess I don't have to call it t subscript 3 anymore at this point, because we've already expressed T1 in terms of other quantities and T2 in terms of other quantities, so I don't think there's any confusion if we just call this T. So T sine theta has to be equal to M1G, and T cosine theta has to be equal to mu static times M2G. If we just divide one equation by the other, T cancels out, sine over cosine is tangent, so tangent theta, the G cancels as well. Tangent theta is M1 over mu static times M2, so if we cross multiply, mu static is equal to M1 divided by M2 tangent theta. And if that represents the minimum amount of static friction, I suppose it works to say that as long as the coefficient of static friction is greater than or equal to that value, then the system will remain at rest. Now, does that match what we were out to prove? Sure does. And let's think about that. This says as M1 gets greater and greater, the amount of friction you would need to hold the system at rest also gets greater. And that's definitely the case. The more weight you hang here, the more friction you would need here, right? Likewise, with M2 in the denominator of this equation, as M2 gets larger and larger, you need less coefficient of friction. And that's just because the heavier this weight is, the greater the amount of contact force it would have with the desk, and therefore the greater the amount of frictional force. Now, what does this equation suggest about the angle theta? As theta gets greater and greater, the coefficient of friction is also going to need to be less. In fact, if you had a case where, well, let's take the ridiculous case. Where instead of being anchored to the wall over here, you've got the ceiling so that the string comes straight up to this point, then essentially the angle is 90 degrees, and this string could go completely slack, and all the tension here would be supporting this weight. So that seems to make sense. In this case, mu static could go to 0, and the system could remain in equilibrium. So the equation that we've proved seems to match up with all the extreme cases. Let's do another problem. One more type of proof. So in this case, there is some amount of friction between the blocks labeled as 1 and 2, but we say there's no friction. The ramp itself is really smooth, and the system again remains at rest. Show that the requirement for the static coefficient of friction between blocks 1 and 2 satisfies this equation. So again, we make free body diagrams in our solution. So for block number 1, there's some amount of normal force. I'll call that N, how about N subscript 1, 2, the normal force, the force of contact between blocks 1 and 2. Okay, pulling up this way, there's some amount of tension. Let's see, what else? Well, there's gravity pulling straight down, but I'm going to break that into components. So there's a component of gravity, m1g cosine theta, and there's a component of gravity back this way, m1g sine theta, and then of course there's some frictional force. Now which way does that frictional force point? We're going to assume in this problem that mass number 2 is greater than mass number 1. So if there was no friction between the two blocks, the system would be accelerating this way, but it doesn't accelerate because there's enough friction to hold it at rest. So without any friction at all, block 2 would be sliding down, block 1 would be moving upward, and so that sliding would create a frictional force back in this direction on block number 1. Okay, let's make a free body diagram for block number 2. There's the same amount of tension pulling it upward, and it has components of gravity, m2g cosine theta, m2g sine theta. There's two normal forces acting on this block, right? It makes contact with the ramp. It also makes contact with block number 1. So there's a normal force this way. Oops. We'll call that N subscript R for the normal force with the ramp. And then there's a force this way, and that's the same one we've labeled here. That's N subscript 1, 2. And then there's friction, right? So which way does the frictional force point? Yeah, it points back up the incline this way. Well, I suppose I should draw the component of gravity down the incline longer so that this whole diagram seems to represent equilibrium. So if the whole system remains at rest, then this tension has to cancel out the combined forces in the other direction. So we can say that T is equal to m1g sine theta plus the friction force. And likewise, that very same amount of tension, when added with the friction force, is balanced by m2g sine theta. So T plus F equals m2g sine theta. Okay, so we can substitute all of this for T in the second equation. So m1g sine theta plus F plus F is equal to m2g sine theta. Notice what we did, all of this right here is the same thing as this T that we substituted for. So 2F is equal to m2 minus m1 quantity times g sine theta when we rearrange, right? F plus F gives us 2F. We subtract this from both sides of the equation and factor out the g sine theta. What can we substitute for force of friction? That's mu static multiplied by normal force. Now, which normal force? It's not the normal force of the ramp that determines the amount of friction force between blocks 1 and 2. It's this normal force we're labeling as N12, which in turn must be equal to m1g cosine theta. So if we call this mu static times normal force of contact between blocks 1 and 2, we're multiplying all that times 2. That's equal to m2 minus m1 g sine theta, but we can substitute for n12 the quantity m1g cosine theta. So 2 mu static times m1g cosine theta is equal to m2 minus m1 times g sine theta. The g can be canceled on both sides. If we divide both sides of the equation by cosine theta, then that cancels out and gives us a tangent theta. So when we solve for mu static, we just need to divide both sides of the equation out by 2m1. So mu static is m2 minus m1 divided by 2m1, all multiplied by tangent theta. Is that what we were trying to prove? Yeah, exactly. Now, does that seem reasonable? Oh, and we can turn the equality into an inequality if we're trying to find all possible values of mu. As long as it's greater than or equal, then the system will remain at rest. So what's this say? What if we had the case where mass 1 and mass 2 were equal? Well, then this would be nothing more than a basic Atwood's machine on a ramp, and as long as the blocks are of equal mass, there'd be no tendency to accelerate at all, so there'd be no requirement for any friction to keep it at rest. And that's exactly what the equation says. If the masses are equal, then this term would go to 0 and no friction would be necessary. This expression also tells us that as mass number 1 gets greater and greater, less and less friction would be required, and that's because with a larger value for mass number 1, the two blocks would be pressed harder into each other. There'd be more normal force, and with more normal force, you get a greater amount of friction given any particular value for the coefficient. And what else does it say? The equation tells us if the angle gets greater and greater, then you're going to need a larger amount of coefficient of friction, and actually if theta approaches 90 degrees, then the coefficient of friction would approach some infinite value, right? And this is like saying if you had these two blocks and they have a pulley coming off of a wall, and then there's a block up against the wall and the string passes over the pulley and the two blocks just touch each other here. Yeah, I don't care how much the coefficient of friction is, if these blocks are unequal in mass, then the system is certainly going to slide. All the normal force would go to 0 if this angle theta is going to 90 degrees, so you get the idea. One last problem. This one's not a proof. This one we just have to find what's the acceleration of the system. So we're given 3 blocks, 2 kilograms, 3 kilograms, and 5 kilograms on a frictionless 30-degree incline. There's no friction between any of these blocks and the ramp, but there is some friction between the 2 kilogram and 3 kilogram. In fact, the coefficient of kinetic friction is given as 0.28. So when released from rest, what's the value of the acceleration of the whole system? So we're going to make free body diagrams. Let's make a free body diagram for the 5 kilogram block. Normal force. We'll call this block, how about A, B, and C. So this is MAG cosine theta. And this is MAG sine theta. There's no friction here, but there is a string pulling back this way. So there's some amount of tension. Let's see, there's going to be 2 different tensions, right? There's some tension in this string and a different amount of tension in the blue string. So maybe we'll call this, how about T and T prime. Okay, so I think that's a correct free body diagram for our 5 kilogram block. So we can say that MAG sine theta minus T represents the net force for that block, and then by Newton's second law, net force is equal to MA. Let's make a free body diagram for block C. So it has some normal force. We'll call this normal force CB. Then there's a component of gravity, MCG cosine theta. There's another component of gravity this way, MCG sine theta. There's a tension pulling in this direction. That's T prime. And there's also some friction, right? Oh, maybe T prime needs to be drawn a little bit longer. Or how about this? We'll draw. The gravity vector is shorter. Okay, and then there's a friction force. If released from rest, we know block C is going to have a tendency to slide up the incline. So there's a force of friction opposing its relative motion with block B going back down the incline. So there's a force of friction F. We know that the normal force between block C and B is equivalent to mg cosine theta. So all we're left with is forces that lie parallel to the incline. And so the force in the direction of acceleration is T prime. And the 2 forces that add up opposite that direction are friction force plus a component of gravity. So since that represents the net amount of force, we can set it equal to MA. Okay, the free body diagram for block B is a little more challenging. I'm going to do a resolved and an unresolved free body diagram. Okay, so its weight vector points straight down. So that's mass of block B times G. There's 2 normal forces. There's the normal force with the ramp, and then there's also block C pushes from above onto block B. So that's the one we labeled before as NCB. Okay, so we got weight, we've got normal force, there's tension, and of course there's also some friction. And the frictional force for block B points in which direction? So if you place your hands together to simulate blocks C and B, then we're imagining how does the way in which block C rubs against block B, how does that impress force upon block number B? So that pulls back up in this direction, right? So there's force of friction here. Okay, so all we need to do is resolve this free body diagram, and the only force that needs to be broken down into its components is the weight vector. So if we keep everything else the same, there's the normal force on the ramp. Now there's going to be two forces this way, right? Normal force, the contact between C and B, and that's going to add with one of the components of the weight of block B. So this is going to be MBG cosine theta. Okay, then the other component to the weight points this way. So that's MBG sine theta. And then pulling back up in this direction are two forces, T plus F. We know these are going to cancel each other out, and so the force in the direction of the acceleration minus the forces opposite the direction give us our net force. So MBG sine theta minus T plus F is equal to mass times acceleration. So we can add all three of these equations together. On the left side of the equation, we can factor out A. So A times the quantity MA plus MB plus MC is all equal to, okay, well, and let's be careful here. I believe this is T prime. Oh, and I just realized I'm missing a force on this free body diagram, aren't I? This is T prime, right? The amount of tension that pulls on block B up in this direction is the one we labeled as T prime. I left out this force T pulls down the incline, right? So that goes in this diagram. You catch that? Yeah, I missed this force in my first attempt, but I see it now. So how do we add that in here? Correct my mistake. This is a T prime, but I also have a plus T right here, okay? Plus T. Right, so this negative T and this plus T cancel out. This T prime and this minus T prime cancel out. So we have, in the direction of motion, two positive forces. We have MA plus MB quantity times G sine theta, G sine theta, G sine theta, yep. And then we have minus F, another minus F, and a minus MC G sine theta. Oh, so I could throw that minus MC in with here. And then we have minus 2F. Okay. So A times MA plus MB plus MC is equal to, now what can we substitute for F? Well, mu times normal force. But which normal force? The normal force of contact between blocks C and B. That's the only place where there's any friction. But that normal force of contact is equal to mcg cosine theta. So instead of writing this as 2F, I'm going to write it as 2 mu n. And instead of 2 mu n, I'm going to write it as 2 mu mcg cosine theta. So now I can factor out a g, and we have g times the quantity ma plus mb sine theta minus 2 mu MC cosine theta. Let's rewrite that. A is equal to G times the quantity, and it's no surprise in the denominator is nothing more than the mass of the whole system added up. And in the numerator, MA plus MB, oops, I forgot my minus MC, minus MC, all multiplied by sine theta, minus 2 mu MC cosine theta. Okay, so A is equal to G. Now we need to make a final numerical calculation here. Let's see if we remember what all these masses are. Mass A is 5 kilograms, mass B is 3 kilograms, and mass C is 2 kilograms, and our angle is 30 degrees. So this is 5 plus 3 minus 2 times sine of 30, which is 1/2, minus 2 times 0.58 times 2 cosine of 30 degrees, all divided by 5 plus 3 plus 2. Okay, so let's see, 5 plus 3 is 8 minus 2. This is 6. 1/2 of 6 is 3. 5 plus 3 plus 2 gives us 10. I'm going to need a calculator for this part. 2 times 0.58 times 2 times cosine 30 gives us about 2. Oh, so our acceleration here is very nearly equal to just 1/10 g, about 1 meter per second squared. That problem's about as challenging as it gets because the free body diagrams are pretty involved, especially the free body diagram for block B. And you noticed I almost made a mistake, right? I had incorrectly labeled this originally as T instead of T prime, and I had accidentally left out the other T here. There's a lot of opportunities to make mistakes. I think I forgot to carry out this minus MC in part of my work as well. So you can see the opportunity to make mistakes is abundant when working with systems of equations of this sort. But if you're very careful and you double check all your work as you go and you inspect your free body diagrams carefully, you should end up with the correct value. So thanks for watching.